These are the solutions on Kepler's laws, questions on Kepler's laws, specifically Kepler's third law. So you need to know the definitions for first, second, and third for most specifications. So most specifications, again, will expect you to derive Kepler's third law from first principles. So we went through this in the lesson, so we can write out each stage. So we start off with the law of Newton's law of gravitation. So the force of gravitation, which is this expression, provides a centripetal force. And we can simplify this. We can get rid of the little m and maybe one of the r's as well. And we need to get rid of the v because there is no expression for velocity in Kepler's third law. So even though Kepler's first law states that the orbit is elliptical, we take the average distance, so we assume that it is a circular orbit. So v equals s over t would be the circumference, 2 pi r. So we need to substitute this into the first expression over here. So we end up with this thing here. So we've already cancelled the m's, get rid of those. Get rid of one of the r's over here. And hopefully you can see, that's not working. Hopefully you can see that the t squared comes from this. And once we get rid of one of those r's, which I can't seem to do, that will give us r cubed. And then we're pretty much there. So we just need to rearrange it to make t squared the subject. So normally we would write t squared on one side and then r cubed on the other with this constant expression here. But if you wrote it the other way with r cubed on its own, then you can have all of this stuff in brackets on the other side, but the reciprocal. So either way is fine, but this is probably the more normal way. So you need to know this derivation for the exam, very important. Question 2 is your standard calculation with Kepler's third law. So we're given the orbital radius, in this case of Mercury. We're told the mass of the sun. We're trying to work out the orbital time period. Okay, so we can write out Kepler's third law. So I've made t the subject. So it's the square root of everything on the right-hand side. And then we just substitute. So the 4 pi squared is constant. So we're dividing by g and the mass. And then we're multiplying by r cubed. So all of this cubed. So there's nothing particularly difficult about this. However, your calculator technique does need to be confident. So there's a lot of numbers, big numbers, small numbers, standard form, cubes and square roots. So it's very easy to make a mistake here. So yeah, do be careful with putting the numbers into your calculator. And the answer in seconds is a little bit meaningless unless you're very familiar with large numbers of seconds. So sometimes we would convert that into years, bearing in mind we're talking about Earth years. And that is something to consider. So hopefully the exam question will not try to catch you out by just saying years when they mean years on Mars or years on Mercury. So if we see the word year, we would assume that it's Earth years, but we could be very specific about that. So that makes a bit more sense, and that should coincide with our understanding. So Mercury is much closer to the Sun than Earth, and it's traveling much more quickly. So its orbital time period will be less. Question 3 is very similar to question 2, but in this case, we're told the orbital time period, and we need to calculate the distance. Okay, so it's basically the other way around. So once again, we can write Kepler's third law. Now we need to rearrange to make r the subject. So we're trying to find the cube root of all of this. So we take gm from the bottom to the top, 4 pi squared from the top to the bottom, and it's the cube root of all of this. So once again, once we've got to this stage, there's nothing particularly difficult about this apart from the fact it's very easy to make a mistake. Also, we've got Earth days, so we need to convert that into SI units of seconds. So we have 687 times 24 times 60 squared. So that's a calculation we need to do. G and M were given, and then it's the cube root. Hopefully you're confident with doing that on your calculator. And again, we get this really big number. Watch out in the question. It might say meters, it might say kilometers, and it'd be really frustrating to lose that easy final mark by forgetting to divide by 1,000. So always check what units the question is asking for. So we get this rather large distance here. Question 4 is more difficult, certainly. Now, if we have been given the mass of the sun, then this will be relatively straightforward. Now, you could answer this by calculating the mass of the sun, because if we know the orbital distance of the Earth, and obviously we know the time period, that's 1 year in seconds, and we could use that information to calculate the mass of the sun. So that is one way of doing it. However, I want you to take a mathematical approach. So assume that we don't know the mass of the sun, and we actually don't need to know it. So this is more like an A star question, where we're not just sticking numbers into a formula, which is hard enough, but we're actually understanding the mathematical relationship. So Kepler's third law, as we know, is this statement here. The time period squared is proportional to the mean orbital radius cubed. So if that's true, even though we don't know what the constant of proportionality is, I can rearrange this and say t squared divided by r cubed must be equal to some constant. And actually that would be the g's and the m's and the 4 pi r squared. So even if we're assuming we do not know the mass of the sun, if that is a constant, then it must be true that for any planet, this ratio is the same. So t squared over r cubed for Earth, so that is the orbital time period of Earth divided by the mean distance cubed of Earth, will be the same for Venus. So the time period of Venus squared divided by r Venus cubed. So now we know 3 of these values, and we can work out the unknown fourth. We're trying to work out Venus, the orbital time period of Venus, so we can make t squared v, or Venus, the subject. So that's the bit we want on its own. So take the r cubed of Venus up from the bottom to the top on the other side. So we have this expression for Earth multiplied by r cubed for Venus. And then we can stick the numbers in. So obviously we need to calculate t squared. That's the time in seconds of 1 Earth year. We're given the value of r, and we're given the value of r of Venus, and we can work out t squared. Almost there, so then we need to find the square root of that, and we should get this value here in seconds, and we can work out the value in Earth days. Again, we're not expected to know the orbital time periods of all the planets other than the Earth. Obviously, we can work that one out. But I think having a rough idea of what they are is probably useful. So Venus is closer to the sun than the Earth is, so it's going to have a slightly shorter year time period. So it's a little bit less than 365 Earth days. So I strongly recommend you be confident with this type of approach, because this is, for many examples, this is going to make the distinction between the B and the A, or maybe the A and the A star, to be really, really confident with an algebraic approach.